Hey there everybody, and welcome to a video on section 6.2. In this video I'll be using slides instead of a handout, but it will work the same way. You should still take notes. There are still exercises for you to do, things like that, and these slides will be posted on Moodle. So in this video I'll cover section 6.2, which is about using integrals to calculate solids, or volumes of solids. So the point of today is to show how integration can be used to calculate the volume of a certain kind of solid, called a solid of revolution, and this is in contrast to calculating the area of a region. So in this section, we get solids of revolution by revolving around a horizontal axis, and then we finish up the course in 6.3 by revolving around vertical axes. So let's start by just thinking about what a solid of revolution is. So here's an example of a specific region. So let's let R be the region enclosed by the root function, and x equals 1. So here's the graph of square root x, and then here's x equals 1. These guys enclose a region here, trapped between the x-axis on the bottom and root x on the top. If we spun or revolved this region around the x-axis, we would get what's known as a solid of revolution. So what you have to imagine doing here, you have to imagine a movie happening. You take this two-dimensional shape and then sweep it out of the screen and then back behind the screen to form this bowl right here. And if you want to see that happening, I've posted a link to this little applet on Moodle. I should warn you ahead of time, this applet is kind of slow, so be prepared for it to frustrate you sometimes. But the nice thing about this applet is it lets you see this movie happening of forming a solid of revolution. So there are lots of things you can control here. You can control the viewing window, like you can go from 0 to 2, 0 to 3, whatever. Just drag these little dots around. You can control the top curve and the bottom curve. So for us, the top curve is root x and the bottom curve is 0. You can control the axis of revolution. So for some reason this applet has a k instead of a y. I'm not sure why that is, but this is saying y equals 0 would be your axis of revolution. Anyways, you can enter all this stuff in, and then you can ask it to revolve. And the nice thing about this over here is you can spin it so you can get a different perspective on what's happening. So it takes that two-dimensional region and it just sweeps it forward and then back behind the computer screen or the whiteboard or whatever. And in this case, you get a nice looking little bowl or the top of a bullet or something. So that's what a solid of revolution is. You take some two-dimensional shape in the whiteboard in the XY plane, and then you take that shape and let it sweep forward and then back behind to create a solid. So the first thing I want to think about is if you want to calculate the volume of a solid of revolution like this, let's take just sort of like a representative little x value. So x here could be a half, could be a third, could be 1, doesn't matter. Just here's sort of an arbitrary little x value. From this little x value, let's form a rectangle like this, which is the classic thing to always do with integrals. Take a little representative rectangle. And then if we let this little representative rectangle do the same sort of sweeping action, sweeping up and then back, it would sweep out, in this case, a disk with a tiny little bit of thickness to it. And we can let that thickness shrink to 0 if we want to. So this delta x could sort of shrink to 0, making just a flat disk. So let me ask you, what is the volume of this disk with a tiny little bit of thickness? Well, the volume of this little disk with some thickness is the area of this circle times the thickness. So what's the area of a circle? It's pi r squared. So here's pi. What's the radius of this circle? Well, the radius is the length that starts in the middle and then goes to the edge. So it's this length right here. But what is that length? It's just the height of this rectangle. Well, what's the height of this rectangle? Well, as we've seen many times before, right? If you start on the x-axis and then go up to a function, that corresponding length, which would be the height of this rectangle, is just given by the function itself. So if this were x equals half right here, then this height or this length or whatever you want to call it would be square root of a half. If x were over here at a third, then this length or height would be root 1/3. This height right here is root 1. This height right here is root 0.75 and so on. Okay, so what's the area of the circle? Well, depending on where your x is, this radius value would be root x and then pi root x squared. So pi r squared is the area of the circle, and then delta x is that little bit of thickness. So if you let that little bit of thickness shrink to 0 and just get like a literal disk, the area of that disk would be pi r squared, where the r value is root x. So given that observation, how would you figure out the volume of the solid of revolution? Well, you can imagine just starting from left to right, working your way from left to right, and then just picking a bunch of little x values. So x1, x2, x3, so on. For each of those little x values, there's a little disk like this. And what's the area of that disk? It's pi times root x squared. And you can just add those up. So you can just like stack these disks on top of each other to get yourself the volume of this bowl right here. And that leads to the following observation. So if R is a region trapped between a function f of x, doesn't matter if it's square root of x or not, any f of x, and the x-axis from x equals a to x equal b, if we revolve this region around the x-axis, the volume of the solid revolution is this. So notice this is pi r squared, so pi times the function squared. And then recall that an integral really kind of is just like a big old summation. It's a big old sum symbol on some level. So we're saying go from a to b, and for every single x value, calculate the area of that disk. So again, you're just sort of like stacking these disks on top of each other, moving from left to right, and that's how you can get the volume of this solid. So for that previous example, integral from 0 to 1 pi root x squared is just pi x. If you calculate that like we've been doing, you get pi over 2. So that's the volume of this bowl right here. And you got that volume by just adding up from 0 to 1, just all these little approximating little disks right here. And you get the volume on the nose because you limit. You let the width shrink to 0 via a limit. So this delta x becomes a dx in the limit. Okay, so that's how you can calculate the volume of a solid revolution like this. So now you guys think about this. Let R be the region enclosed by y equals x squared, y equals 0, so the x-axis, or sorry, the y, yes, the x-axis, yes. X equals 1 and x equals 3. Find the volume of the solid of revolution obtained by revolving R around the x-axis. So pause the video and see if you can get this 242 pi over 5 answer. Okay, so hopefully you're able to get that using the same sort of integral here. Let me show you the picture, just because it's fun to look at. So I'm doing x to the second now. Oops. X to the second from 1 to 3. So I got to adjust these little values here from 1 to 3. Let me unrevolve it. Okay, so let's watch the movie and see what kind of shape we get. Do I try to zoom out? Maybe. Here we go. Again, this thing is kind of slow. Let's zoom out and see if we can see what's happening. Okay, so it takes that region and revolves it around. It kind of takes its time doing it. So in the end, what I think you'll get, so you can see the bottom of it is a disk. I think in the end what you'll get is sort of a volcano-looking shape, like a filled-in volcano. So if you spin it around, yeah, see that? Or a symbol, I guess if you like a musical symbol. Anyway, to me it looks like sort of a volcano. So the question is, what's the volume of that volcano? Well, it turns out it is 242 pi over 5. So hopefully what you did was, you did the integral from 1 to 3 this time, and now pi r squared. What is the radius value now? The radius value now is this function, x squared. So you do x squared squared. So hopefully what you did was you integrated 1 to 3 pi x to the 4th, x squared squared. And that'll give you this 242 pi over 5. Okay, well, what kind of other regions could you get and revolve around a horizontal axis? So now let's let R be a region trapped between two curves, sort of like the previous section here, between y equals x and y equals x cubed. So we're not doing trapped between a single curve and the x-axis. How would you find the volume of such a solid now? And again, the picture is still the same. You still take your little region and you still spin it around. So we can again watch a movie of this. So let's type in, so y equals, oops. Okay, so this is the top curve. So x was the top curve and then x to the third was the bottom curve, like that. And I'm going from 0 to 1. See, there's a tiny little region that it's enclosed by. Now let's see if it'll let me zoom in. No, not zoom out. In and in. Yeah, be real delicate with this, or sometimes it just freezes everything. Okay, so let me unrevolve it, and let's watch the movie here. Let's watch it from the side. So it's going to take this little region here, and revolve it around the x-axis. Okay, so it's a little hard to see from this perspective, but it's trying to color code it for you. See, it's not totally filled in, right? It's not like just a pyramid or something. So you get this sort of little hollowness in between. So the cross section, whoa, what just happened? The cross section you get, if you were to slice any part of this, is this tiny little moon slice here, caught between x cubed and x. See, the color coding you see is like it's kind of, it's like the what's it called? The horn of what is that thing called? At the end of a trumpet. It's like the end of a trumpet. I don't know. You know, so it's hollow, right? And it kind of goes inside. That's driving me nuts. I can't think of it. The bell of a trumpet? That's not right. Sorry if you musician students who know what I'm talking about, but are mad that I don't know the word. Okay, so now the thing is, in the previous example here, when you took a little x slice of your little curve and revolved it around, you got this solid object here. You got this disk with a tiny bit of thickness. But now there's like a hole in the middle of our object. So now if you take a little x slice and revolve it around, you don't get a disk anymore. There's this hole, there's this gap. You get what's called a washer, like a literal washer that you could buy at the hardware store. So sometimes when you do these revolving things, you don't get disks. Sometimes you get disks with holes in the middle, right? There's like a little chunk taken out of this disk. So now we have to think about what the area of a washer is. So here's a washer. Every washer has like an inner radius and an outer radius, and here's a side view if you want to see that, right? Like a 3D side view. So the area of this overall object here, and by the way, in high school geometry, they call these things like an annulus. So you might see that word also. So the area of an annulus is you take the outer circle's area, which is pi capital R squared, and then take out the inner circle's area. So you just literally take that middle circle, that smaller circle, out of the bigger circle. So that's what the area of a washer is. So now in this example here, we would take little x slices going from left to right, and now we have to have areas of washers instead of areas of disks as we go. Okay, so in the example from this previous slide, the radius would be, sorry, this should say area, right? The area is pi outer radius squared minus pi inner radius squared. So here, if you're going from the x-axis all the way to the edge of the object, you're going from the x-axis to y equals x. That's the outer radius. If you're going from the x-axis to the closer curve, x cubed, that inner radius is x cubed. So, sorry, this should say the area. The area is pi x squared minus pi x cubed squared. So again, this big R is x. This little r is x cubed. So again, it's hard to see this without drawing a picture. So if I were you, I'd always draw a picture like this when you're given a couple of curves like this. So again, you can just imagine like, okay, so if I start at the x-axis and walk up, it takes me x cubed worth of distance before I hit this first curve. And that's when my washer sort of comes online, right? Because before that, I didn't have anything. It's just a gap. So this distance from the x-axis to the orangish curve here is x cubed. And if I keep walking, the total distance to the outer edge of the washer is x. Okay, so the outer radius is just how far you have to walk to get to the outer edge of the object, and the inner radius is how far you have to walk to get to the inner edge. So shape starts, washer starts here, washer ends there. Where the washer ends is the outer radius, where the washer begins is the inner radius. And you end up with an integral like this. So you're going from 0 to 1. So this again is just the area of a washer. If you integrate that, you get this. So you do your antiderivatives. This is x to the 6th right here. So you get next to the 7th over 7. And you end up with 4 pi over 21. Okay, so in general, in this section, you could get disks, but you could also get washers, right? You could have a disk with a hole punched through the middle of it. So I want to show you one more example and then have you guys try another one on your own. So that previous example, what if we revolved this thing around the line y equals -1? Which is the x-axis but down 1. What would you get now? So let me just show you a picture of that. So again, this slider here, this purple slider, lets you choose the axis of rotation. Okay, so here's y equals -1 right here. And can you see what happened? It just like punched a hole through the middle of the object. So if I unrevolve this, come on, then ask it to make the movie again. See, it sweeps out the little moon shape, but now it's sweeping around the line y equals -1. And you get that same kind of shape that we had before, like the end of a trumpet, but now it's like a much bigger hole. And I could keep doing this, right? I could keep making it bigger. See if it'll let me zoom out. Nope, out. So you can see the whole thing. There you go. And so on, right? So as I keep asking it to revolve around like things that are farther away from the original shape, I just keep adding more and more space. But anyway, this problem asked about y equals -1. So there's that. Y equals -1 is shooting right through the middle of it. So let's think about what would happen now to this integral. Okay, this integral here. Here, the inner radius was x cubed, the outer radius was x squared. So we did pi r squared minus pi r squared. Well, what happens now if you move the axis of revolution down a unit? So let's just look at a zoom in of that. So here's the little slice we're considering, y equals x cubed up to y equals x. Here's the axis of revolution now. Okay, so the inner radius, as we said before, the inner radius is how far you have to walk from the axis of revolution to where the washer starts. So if I am here at a half, I would have to walk this one full step, and then from a half to the cube curve. So this will be one full step plus 0.5 cubed. And if I want to reach the outer edge of the washer, I have to keep walking up to x here. This is y equals x, so this would be a half. So no matter what x I'm at, so let's think about this little tick mark here. If I want to walk from the axis of revolution to where the washer comes online, I have to take one full step. This distance is 1 right here, because it's from 0 to -1. So this distance is 1, then up to the curve x cubed. So 1 plus x cubed. And then if I want to get to the outer edge of the washer, where the washer ends, again, it'd be 1, but then plus an x. So all that to say, in this previous example, if I want to adjust these radii, because the radii are bigger now, my inner radius was x cubed plus 1, my outer radius was x plus 1. I've just created an extra one step of distance in those radii. So I get this integral here. So the inner radius is x cubed plus that 1 from moving the axis of revolution down one step. And here's x plus a 1 from moving it, again, down one step. So these radii are bigger now. And if you calculate this integral, you get 29 pi over 42, which is actually much bigger than 4 pi over 21. And it should be bigger because you added more space. So you made a shape with more volume, right? This shape here has more volume, like you've swept out a larger range of things than this shape. So the farther you make the axis of revolution from your original shape, the bigger the object will be in terms of volume. Okay, so I want to conclude here by having you guys try one more example. Where am I? Okay, so you try this. Let R be the region enclosed by x squared plus 1, 3x plus 5, and x equals 2. Set up an integral, so don't bother computing at this time. So just set it up. That gives the volume of the solid of revolution when R is revolved around the line, y equals -2. So pause the video and think about that for a minute. Okay, so with any of these problems, it is highly suggested to you that you think about the graph here, right? So graphically speaking, what is happening? So these sorts of curves here, x squared plus 1, 3x plus 5, you're supposed to be able to visualize these on your own, right? These are not exotic functions. So let me clear the deck here. Okay, and let me graph these for you. So here's x to the second plus 1, looks like that. Okay, and here is 3x plus 5, like that. Okay, so you're basically talking about this region here. It's again sort of like a little moon shape or something, a little crescent moon shape. Okay, but then it gives me some additional restrictions. Oh, and x equals 2. Okay, so let's put that in there. X equals 2. Whoops, not y. There we go. x equals 2. Okay, so like this. So here's the kind of shape that I'm talking about. And I just noticed I had the same issue in the previous video. I'm not sure why I can't keep this straight. There's also supposed to be an x equals -1 here. See, just like the last video, I'm not sure why I can't handle this, but there's some ambiguity here. Do you mean this stuff over here, or do you mean this stuff over here? You know, so I meant this stuff over here. So I meant to include an x equals -1. So in your notes or something, put like a comma, x equals -1 here. So sorry about that. On an exam, that certainly wouldn't happen. I don't know why I keep forgetting that here. Okay, so here is the region we're talking about, this right here. And now we need to revolve it around the line y equals -2. Okay, so that's down here, and let me make it a different color. Here, so we can see a little better. Okay. So we're taking this region here, we're revolving it around this red line. So again, you think about like a typical little X slice here, like this little tick mark here. What's the inner radius, what's the outer radius? So since we're doing -2 now, this is -2, then this distance here, this is a full step of size 2. So I take a step of size 2, then up to x squared plus 1. So the overall step size is 2 plus x squared plus 1. And then same thing for going up to this. This full step to the outer edge of the washer is, again, this is step size 2, and then plus 3x plus 5. So you should have gotten an integral. Again, I guess given my initial setup here, the fact that I forgot x equals -1, you would have had to choose, I guess. But your integral should have been like this. Integral from -1 to 2, and then here's the outer radius, adjusted up by 2 squared, minus, here's the inner radius, adjusted up by 2 squared. And since it just said set up, we don't have to calculate that. Now we can see it from the picture, right? But you're not going to see this picture yourself because you're not going to have a graphing calculator. So you have to yourself be able to draw this. And so again, you won't be given exotic functions, right? Like quadratics and linears and things like that. These aren't exotic. So if you wanted to see this, how this worked, you should know that this line slices above this opening parabola, and you can ask, well, where do these things meet? And you figure that out by setting them equal to each other, factors, you know, and you end up with -1 and 4. So that's how you know, oh, my x value would have started at -1, and I'm tempted to go all the way to 4, but this told me not to. It told me to stop at x equals 2. So if you put a 4 up here, right, you're basically just ignoring that I told you to chop it off right here at 2. But you could, of course, go all the way to 4 if the problem were different, and you can still get that volume of that solid of revolution. Okay, so it's unfortunate that we're not in person here because this is kind of a subtle thing to do. It takes some getting used to, this kind of thing, the setting up of these integrals here. But hopefully, like this little applet, which you should feel free to use in the homework, is useful to you to draw these little movies for you. And hopefully, this sort of visualization here that you would draw yourself would lead you to the appropriate radii choices, which will then lead you to the appropriate expression inside the integral. So it's always pi r squared minus pi r squared, except when, you know, there is no inner radius, which is the case way back up here, right? There was no inner radius because we didn't get a hole punched through a disk. Okay, so that's the end of section 6.2. Next time what we're going to do is we're going to do this same thing, but instead of, see how this revolves around the x-axis, we're going to revolve it around the y-axis. So we'll go left-right like this instead of like up-down. And then we'll be done with the course material.